Chapter 11, number 42. You pull downward with a force of 28 newtons on a rope that passes over a disc-shaped pulley of mass 1.2 kilograms and radius 0.075 meters. The other end of the rope is attached to a 0.67 kilogram mass. Is the tension in the rope the same on both sides of the pulley? And if not, which side has the greater tension? Part B says, find the tension in the rope on both sides of the pulley, which sort of implies the answer to A is not the same. If we look at it, the weight of the thing we're talking about, the weight of this mass is about 7 newtons, a little under, 6.7, a little under that, which means we are pulling much harder than the weight of the box. And so we expect the box to be, or the mass to be raised. So ultimately, this entire system is going to rotate with some angular velocity or some angular acceleration alpha, which means there must be an unbalanced torque on the pulley, which is not massless or ideal in this case, and therefore it matters that the difference in torques is going to be I alpha, which means that they can't be equal because the tensions cannot be equal. If we look at the free body diagram for the pulley, we have the tension here that's being caused by the box pulling down. I'll call that FT1. And we have the tension of the rope on the other side, FT2. If we consider this part of the rope, like the part of the rope we're pulling on, that's going to have the force F that we pull down and the tension force pulling back up. But the key thing here is that the rope is essentially massless, and that's going to play a big role for us. And then we say, of course, that this point is accelerating downward. And I guess we should actually put the other mass in. That has an FT1 pulling up and an mg pulling down. It's called m1g pulling down. And then we know that for every centimeter that you pull your hand down, the box goes up. So there's also an acceleration here of the box going up at A. And of course, because that's happening, we have some rotational thing going on, so there's an alpha there as well. From the free body diagrams, we end up with a bunch of interesting statements. For instance, the sum of the forces on box 1, which is FT1 minus the weight of box 1. The sum of the forces on this little thing, which I'll call 2, this massless point of rope, is going to be FT2 minus the force that you're exerting. And the sum of the torques on the pulley is going to be, and now I have a couple of interesting things. We look here and say, hey, the line of action for T1 is of course vertical. The line of action for FT2 is vertical, which means for both of them, the perpendicular distance is just R. So we have, this is FT1R, because that tends to move it clockwise, minus FT2R, because FT2 tends to move it counterclockwise. That's from the diagram. And then, from Newton's second law, we have that the sum of the forces on 1 is m1a. And the sum of the forces on 2 is, and this is the interesting bit, 0 mass times minus a, or 0. It doesn't matter how much acceleration goes on, those two forces have to be in balance because there's no mass. And finally, the sum of the torques is I, and I should be very careful here, we're going counterclockwise, so minus alpha. And it's a disk, so I is a half times m times r squared. And then what we end up doing is using the second law to put those back together. We would just combine them up, which we'll do in a second. So setting those things equal according to identities, we get these three equations. and we get some interesting things that come out. The first thing, of course, is that the tension on the side you're pulling on turns out to be just how hard you pull, which is maybe not surprising, but was sort of interesting. We're also going to have to use, somewhere along the line, that for the rope to not break or bunch up, it must also be true that A is our alpha. So if I go down to this question, which means I can say that alpha is A over R, and so I cancel one set of R's anyway, and I have that this equation becomes ft1 minus ft2 equals minus a half times m times r times a over r, or minus a half m a. But we know from here, we can find here, we can find alpha. Oh, we can find A. And we say, wait a minute, A is ft1 minus m1 g over m1. And that's what we have. Now, the algebra here is not particularly great. We would need to combine up the right-hand side, so we'll say ft1 minus ft2 is minus 1/2, and then attribute all of this stuff. So I'll have m over m1 times ft1 plus 1/2 mg. Yeah. And then now we have to do the goofy thing where we have to bring like this to one side over to here, and then bring this over to here, and we're left with ft1 plus 1/2 capital M over m1 ft1 equals ft2 plus 1/2 mg. And next we're going to factor out this from both terms, so we'll end up with an ft1 out here, and on the inside we'll have 1 plus 1/2 times the ratio of the masses, and all of that will equal f plus, let's get that straight, ft2 really here, remember, is the f that we're pulling with, plus 1/2 mg. So ft1 is going to be f plus 1/2 capital mg over 1 plus 1/2 the ratio of masses. None of this is particularly intuitive to me offhand, and I'm not sure if it's showing us anything particularly big deal, but we have these numbers, so we might as well just put them in and see what happens. And we end up with that ft1 is, after you put all those numbers in, 18 newtons, which, as we expected, is less than the 28 newtons that you're pulling with. You have to pull harder than the box needs to be lifted with, because you in some sense have to, quote unquote, pay for the rotation of the pulley.